Right now, at this exact moment, on the 27th of October 2025, an object from beyond our solar system is moving behind the sun at 152,000 miles per hour, completely hidden from Earth's view, and in 48 hours it will reach the closest point to our star that it will ever achieve. That object is 3I, Atlas, the third confirmed interstellar visitor in human history. And what happened on October 21 at precisely 14:07 UTC should concern every astronomer on this planet. When the comet entered solar conjunction, positioning itself exactly on the opposite side of the sun relative to Earth, something changed. The jet of material that had been pointing toward the sun for 3 months, an anti-tail that violates every textbook description of cometary behavior, suddenly reversed direction. That reversal occurred within the 8-day window between solar conjunction and perihelion, the optimal time frame for what aerospace engineers call an O-berth maneuver, the most fuel-efficient moment for any spacecraft to alter its trajectory. Let that sink in. NASA's Atlas Survey Telescope in Rio Hurtado, Chile first detected 3I Atlas on the 1st of July 2025, moving at 44 kilometers per second with a hyperbolic orbit carrying eccentricity values of approximately 1.000016. Those numbers tell us this object is not gravitationally bound to our Sunday. It came from somewhere else. It's passing through, and it's never coming back. When Discovery observations were announced, the Minor Planet Center had compiled 122 separate measurements from 31 observatories worldwide, with pre-discovery imaging extending back to the 7th of May 2025 from NASA's Transiting Exoplanet Survey satellite. The object was already bright and active at 6.4 astronomical units from the Sun, a distance where water ice remains frozen solid. That early activation indicates sublimation of supervolatiles, compounds more fragile than water, materials like carbon dioxide, carbon monoxide, carbonyl sulfide. The James Webb Space Telescope confirmed this on the 6th of August 2025 using its NIRSPEC instrument. The carbon dioxide to water ice ratio measured 8:1, among the highest ever recorded for any comet anywhere. To understand what that means, consider this. Our own solar system's comets typically show ratios closer to 1:10 or 1:20. 3I Atlas is chemically backward. It formed in conditions we don't see here. It's a chemical fingerprint from another stellar neighborhood, and that fingerprint doesn't match ours. The Hubble Space Telescope imaged 3I Atlas on the 21st of July 2025 when the comet was 277 million miles from Earth, revealing a teardrop-shaped cocoon of dust streaming from the nucleus. By August 20, refined photometry constrained the nuclear diameter to between 440 meters and 5.6 kilometers. Think of that uncertainty, a factor of more than 10 in possible size. For an object moving this fast, carrying this much mass, that's the difference between a neighborhood and a city. Later analysis pushed the minimum diameter toward 5 kilometers, suggesting total mass exceeding 33 billion tons. At perihelion on October 29, solar illumination will deliver more than 33 gigawatts of power to its surface. That's equivalent to at least 1/3 of the total power generated by 94 operating commercial nuclear reactors in the United States, the largest producer of nuclear power in the world. And all that energy is hitting an object we can't currently see because it's hiding behind the Sunday. Here's where things get interesting. ESA's Mars Express and ExoMars Trace gas orbiter observed 3I Atlas during its closest approach to Mars on the 3rd of October 2025 at 4 UTC, when the object passed within 30 million kilometers of the red planet. The high-resolution stereo camera aboard Mars Express and the color and stereo surface imaging system on the trace gas orbiter both captured images. Those images showed faint features around 3I, Atlas, that ESA initially described as likely noise artifacts, no verified fragments, no debris field, no secondary objects clearly associated with the primary nucleus. The spectrometers, NOMAD on TGO and Omega plus SpyCam on Mars Express, attempted to measure molecular signatures, but the signal was too weak for full spectral characterization. What they could measure showed continued outgassing, continued activity, but nothing that definitively screamed fragmentation. A comet under this much thermal stress, moving this fast, carrying exotic volatiles, should be shedding material asymmetrically. Jets should be acting like thrusters. Rotation rates should be increasing. We've seen this before with Comet 332P, Ikeya Murakami, which spun itself apart. We saw it with Shoemaker-Levy 9, torn into fragments by Jupiter's gravity before crashing into the planet in 1994. Natural processes exist that destroy comets. 3I. Atlas is not showing those signatures, not yet. On October 21, the comet reached solar conjunction. For observers on Earth, it disappeared behind the sun, entering a region within 10 degrees of solar elongation, where scattered sunlight overwhelms any reflected signal from the comet itself. Ground-based observations became impossible. Space-based assets positioned away from the Earth-Sun line could theoretically observe during this window. ESA's solar orbiter operates between 0.3 and 0.9 astronomical units from the Sunday. NASA's Parker Solar Probe reaches perihelion at 0.046 astronomical units. Neither mission publicly announced observation plans for 3I Atlas during solar conjunction. Why? Resource allocation, power budgets, thermal constraints. These spacecraft have primary mission objectives. Chasing an interstellar comet during the most thermally stressful part of its trajectory wasn't in the original plan. So we have an 8-day gap. Solar conjunction on October 21. Perihelion on October 29. 8 days when the object is closest to the sun, moving fastest under maximum thermal load, and completely unobservable from Earth. That's the window. Now let's talk about the Oberth effect, because understanding this matters. When a spacecraft, or any object, is moving through a gravitational field, its kinetic energy depends on velocity. If you burn fuel to change velocity, the kinetic energy change is proportional to velocity. Therefore, the most efficient time to burn fuel is when you're already moving fastest. That happens at closest approach to a massive object. For 3I, Atlas at perihelion, orbital velocity peaks at 68 kilometers per second relative to the Sunday. A small velocity change, a delta V of just a few kilometers per second applied at perihelion, could dramatically alter the outbound trajectory. To shift from the current path to an intercept course with Earth's orbit would require changing the orbital radius by approximately 0.36 astronomical units. The math works out to a delta V on the order of 24 kilometers per second for a significant course correction, but even a fraction of that, applied correctly, could redirect smaller payloads, mini-probes, sub-satellites. Anything deployed from a mothership during this window would benefit from maximum gravitational assist. This isn't speculation. This is orbital mechanics. The Oberth effect is how we slingshot spacecraft past planets to reach the outer solar system. It's textbook astronautics. The question isn't whether the physics allows it. The question is whether anything is using it. Let's enumerate the anomalies, because individually they're interesting, but collectively they form a pattern that's harder to dismiss. First, trajectory alignment. 3I, Atlas, follows an orbit within 5 degrees of the ecliptic plane, the disk containing our solar system's planets. Interstellar objects should arrive from random directions distributed isotropically across the celestial sphere. The probability of an object arriving so closely aligned with our planetary plane by pure chance is low. Not impossible, but worth noting. Second, velocity. At discovery, 3I, Atlas, was moving at 44 kilometers per second, faster than 1I, Oumuamua's 26 kilometers per second, or 2I, Borisov's 32 kilometers per second. It's the fastest known object ever observed within the solar system. Third, early activity. The comet was bright and active at 6.4 astronomical units, indicating volatile sublimation far beyond where water ice becomes unstable. Fourth, chemical composition. The 8:1 carbon dioxide to water ratio is extreme, suggesting formation in an exceptionally cold protoplanetary disk, far from its parent star. Fifth, the antitail. From July through August, 3I Atlas displayed a jet of material pointing toward the sun, not away from it. Antitails are rare but not unprecedented. They occur when dust particles lag behind the comet's orbital motion and create a forward-pointing fan when viewed from certain geometries. But observations from the Nordic Optical Telescope in the Canary Islands confirm that this antitail persisted for weeks and then, in September 2025, reversed to a conventional tail. That transition coincides with the approach to perihelion. Sixth, structural integrity. Despite thermal stress equivalent to 1/3 of US, nuclear power output focused on a 5-kilometer object, 3I, Atlas, shows no clear evidence of fragmentation. The total mass loss from July through October amounts to approximately 2 million tons, less than 0.00005 of its total estimated mass. That's ablation of a surface layer averaging 4 centimeters thick, barely the skin. Seventh, planetary encounters. The trajectory brings 3I Atlas within tens of millions of kilometers of Mars, Venus, and Jupiter, while remaining over 160 million miles from Earth at closest approach. This isn't a near miss, this is a grand tour. Eighth, timing. Discovery occurred in early July. Solar conjunction in October. Perihelion 8 days later. The entire observational campaign is compressed into a 4-month window, with the most critical phase occurring when Earth-based telescopes are blind. Now, 3 scenarios. Scenario 1, natural comet. 3I, Atlas is exactly what it appears to be, a chunk of ice and rock ejected from another star system, probably by gravitational interaction with a giant planet or close encounter with a neighboring star. The chemical oddities reflect formation conditions different from our own solar system. The early activity indicates volatile-rich composition. The antitail is geometry and dust lag effects. The structural integrity is fortunate but not impossible. Comets are tough. Some survive multiple perihelion passages. The trajectory alignment is coincidence. Space is big. Orbits are random. If you observe enough objects, eventually one will align with the ecliptic. This scenario requires no new physics. It fits within known comet behavior. It's the conservative interpretation. Probability? High. This is the null hypothesis. Scenario 2, warning or beacon. 3I. Atlas is natural, but the timing of its discovery and the attention it's generating serve as a focusing event for our species. The universe is sending us a visitor, and whether by design or accident, that visitor is arriving at a moment when our detection capabilities are improving rapidly. The Vera Rubin Observatory just came online. Atlas is scanning the sky continuously. Test captured pre-discovery observations. We're getting better at spotting these things. Perhaps what seems like perfect timing is actually observation bias. We're seeing it because we're finally looking hard enough. If Rubin had started operations 2 weeks earlier, it would have detected 3I Atlas before Atlas did. This scenario suggests that interstellar objects are more common than we think, passing through our solar system constantly, and we've only just begun to notice. The Allen Telescope Array at the SETI Institute began radio monitoring on July 2, searching for narrowband emissions, any hint of artificial signals. None detected. Silence isn't evidence of absence, but it's not evidence of presence either. If this is a beacon, it's not broadcasting on frequencies we're listening to. Scenario 3, reconnaissance. 3. I-Atlas is not natural. It's a probe, possibly a mothership, carrying smaller payloads, using the Oberth maneuver at perihelion to deploy assets toward inner system targets. The anti-tail wasn't outgassing, it was deceleration thrust, slowing down for optimal trajectory insertion. The reversal to a conventional tail in September represents a shift from braking to acceleration, or simply cessation of thrust. The chemical signature, the CO2 to water ratio, isn't about formation conditions. It's propellant. Carbon dioxide sublimes at low temperatures, providing thrust without complex machinery. The structural integrity isn't luck, it's engineering. The trajectory alignment isn't coincidence, it's planning. The 8-day gap during solar conjunction is cover. Whatever happens at perihelion happens out of sight. And when 3I Atlas reemerges in November, we'll see what's left or what's been released. This scenario requires intention. It requires technology. It requires us to accept that we're not alone and that someone, somewhere, has sent hardware into our cosmic neighborhood. Probability? Low, but non-zero. This is the black swan, a small probability event with enormous implications. The evidence doesn't support scenario 3. Let's be clear about that. Everything we've observed can be explained by natural processes. The anti-tail is consistent with dust particle dynamics. The chemical composition is unusual, but not impossible. The trajectory is coincidentally aligned, but not impossibly so. The lack of fragmentation is fortunate, but comets do survive perihelion. Radio observations detected no artificial signals. Spectroscopic analysis shows volatile sublimation, not exhaust plumes. Image analysis from Mars orbiters revealed no structured components, no geometric patterns, no clear evidence of technology. We have a comet. That's what the data says. But here's the thing about low probability events. They're low probability until they happen. And when they do happen, they rewrite everything. The Galileo Project, led by researchers at Harvard University, maintains ground-based observatories monitoring unidentified objects in Earth's atmosphere and space. Their protocol for assessing potential artificial origins relies on multiple criteria: structured geometry, anomalous acceleration not explained by gravity or outgassing, electromagnetic emissions in non-natural frequencies, material composition inconsistent with known comet or asteroid classes, and trajectory adjustments not attributable to gravitational perturbations or volatile jets. 3I. Atlas scores high on trajectory oddities and chemical composition, but shows no clear evidence of structured geometry or anomalous acceleration. The anti-tail-to-tail transition could be interpreted as thrust cessation, but it could just as easily be changing geometry and solar radiation pressure. The problem with distinguishing natural from artificial is that good engineering often mimics nature. A probe designed to look like a comet would behave like a comet most of the time. You'd only catch the discrepancies during critical maneuvers. And those maneuvers would ideally occur when nobody's watching. The 29th of October, 2025, perihelion, 203 million kilometers from the Sun, just inside the orbit of Mars. At that moment, 3I, Atlas, will be traveling at maximum velocity, under maximum thermal load, and completely hidden behind the Sun from any Earth-based observer. If this object is natural, perihelion is when fragmentation is most likely. Thermal stress will peak. Volatile jets will be most violent. Rotation rates will be maximum. If it survives intact, we'll know in November. If it breaks apart, we'll see a debris field. If it deploys something, we'll see secondary objects separating on different trajectories. The tidal force from the Sun would separate those trajectories over the following weeks and months, making any deployed objects easier to distinguish from the primary nucleus. ESA's Jupiter Icy Moons Explorer, JWST, will pass within 64 million kilometers of 3I, Atlas, on the 4th of November 2025, 5 days after perihelion. JWST carries the Janus Visible Imager, MAGIS infrared spectrometer, and SWI submillimeter wave instrument. Those instruments will provide the first post-perihelion data. The first look at what 3I Atlas looks like after its closest approach to the Sun. Data downlink is expected in February 2026 because JWST is currently on the far side of the Sun using its high-gain antenna as a heat shield. It's transmitting on its medium-gain antenna at reduced data rates. So we wait. NASA's Juno spacecraft, currently orbiting Jupiter, will have its closest observation opportunity on March 16, 2026, when 3I Atlas passes within 54 million kilometers of the gas giant. Juno's ultraviolet, infrared, and radio instruments can characterize composition, measure thermal emission, and search for any electromagnetic activity. By March, 3I Atlas will be outbound, cooling down, activity declining. Whatever is going to happen will have already happened, but Juno can tell us what the object looks like after perihelion, whether it fragmented, whether its activity profile matches predictions, whether anything unexpected occurred. From Earth, 3I Atlas will re-emerge in early November, visible in the morning sky through amateur telescopes. First observations are expected around the 11th of November, 2025, when the comet rises about 2 hours before the Sun with predicted magnitude around 10. That's dim, but accessible to experienced amateur astronomers with decent equipment. Professional observatories will resume tracking. The Hubble Space Telescope is scheduled to perform ultraviolet spectroscopy in November to measure sulfur to oxygen ratios and gas emission compositions. Ground-based spectrometers will analyze outgassing rates in chemistry. Photometric monitoring will track brightness variations and search for fragments. By mid-November, we'll know if the comet survived perihelion intact, if it shows conventional post-perihelion behavior, if its activity curve matches models. By December, when 3I Atlas reaches closest approach to Earth at 169 million miles on December 19, we'll have months of post-perihelion data. That's the critical observation window, November and December 2025. That's when we find out what 3I Atlas really is. So what should we look for? First, fragmentation. If chunks separate from the main nucleus, we'll see them. They'll have slightly different trajectories. Over weeks, those differences add up. Tidal forces from the sun amplify separation. If 3I Atlas releases mini probes at perihelion, by November those probes would be tens of thousands of kilometers from the primary nucleus, potentially on diverging paths. Look for secondary objects. Second, trajectory changes. If the comet performs a maneuver, its outbound trajectory will differ from predictions. Gravity-only models allow precise orbit determination. Any deviation indicates non-gravitational forces. For a comet, that's usually outgassing. Jets of volatile material act like tiny rocket engines, nudging the nucleus. But if the deviation is larger than outgassing can explain, or if it's directed in ways inconsistent with solar heating patterns, that's anomalous. Third, activity changes. After perihelion, comet activity typically declines as the object moves away from the sun and cools. If 3I Atlas shows increasing activity post-perihelion, or if new jets appear in unexpected locations, that's worth investigating. Fourth, electromagnetic emissions. The Allen Telescope Array will continue monitoring. If artificial signals appear, that's definitive. But absence of signals isn't definitive in the other direction. A probe might not broadcast, or might use frequencies we're not monitoring, or might communicate in ways we don't recognize. Fifth, structured components. If high-resolution imaging from JWST or Juno reveals geometric patterns, surface features inconsistent with natural erosion, regular spacings, anything that looks manufactured, that's evidence. But again, absence of obvious structure doesn't prove naturalness. Good engineering can be subtle. The improbability stack. This is the framework for assessing extraordinary claims. Each anomaly has a probability. Trajectory alignment within 5 degrees of the ecliptic, maybe 10%. Extreme chemical composition, maybe 5%. Early activity at 6.4 AU, maybe 15%. Anti-tail persisting for weeks, maybe 20%. No fragmentation despite thermal stress, maybe 30%. Perfect timing of solar conjunction and perihelion, maybe 20%. Fastest known object in the solar system, maybe 5%. Grand Tour trajectory past multiple planets, maybe 10%. If these probabilities were independent, you'd multiply them together. 0.1 times 0.0, 5 times 0.1, 5 times 0.2 times 0.3 times 0.2 times 0.0, 5 times 0.1 equals 0.0000000045, or about 1 in 200 million. But probabilities aren't independent. A high-velocity object from the outer galaxy might naturally have unusual chemistry. An ecliptic-aligned trajectory might coincidentally bring it near multiple planets. Absence of fragmentation might just mean the nucleus is structurally sound. Each piece of the puzzle has conventional explanations. It's the combination that raises eyebrows. And even then, low probability isn't zero probability. Rare events happen. We call them rare because they're infrequent, not because they're impossible. The institutional response has been measured. NASA's official statements emphasize the scientific opportunity to study an interstellar object, the third in history, the first since 2I, Borisov in 2019. ESA coordinated observations across multiple missions, Mars orbiters, JWST, potentially Hubble. The SETI Institute initiated radio monitoring but found no signals. Academic papers are appearing on preprint servers, analyzing composition, trajectory, activity profiles. Some researchers, notably those affiliated with the Galileo Project, have publicly stated that the possibility of artificial origin should be considered seriously given the object's anomalies. Other researchers have pushed back, arguing that all observed features are consistent with natural processes and that invoking extraterrestrial technology is premature and unnecessary. This is how science works. Evidence, interpretation, debate. The data is public. Observation logs are shared. Anyone can download orbital elements, spectroscopic data, imaging from Hubble and JWST. Transparency is the rule, not the exception. If there were clear evidence of something non-natural, it would leak. Thousands of astronomers worldwide are tracking this object. Suppressing information isn't feasible. What we're seeing is caution, not conspiracy. Scientists don't want to cry wolf. Extraordinary claims require extraordinary evidence. Right now, the evidence is intriguing but not extraordinary. Let's address the elephant in the room. Why does this matter? If 3I, Atlas, is a natural comet, it's still valuable. It teaches us about planetary formation in other star systems. It shows us chemical compositions we don't see in our own neighborhood. It tests our detection capabilities and observational infrastructure. It reminds us that the galaxy is old and material moves between stars, and we're part of a larger cosmic ecosystem. If 3I, Atlas, is something else, if it's reconnaissance, if there's intention behind the trajectory, then we're looking at first contact, not radio signals, not exoplanet biosignatures. Hardware, actual hardware from another civilization operating in our solar system right now. That would be the most important discovery in human history. It would confirm we're not alone. It would tell us that intelligence arises elsewhere, that technology develops, that spacefaring civilizations exist or have existed, and that they've sent probes across interstellar distances to explore other systems. It would raise immediate questions. Who sent it? From where? How long has it been traveling? What's its purpose? Is it still operational? Can we communicate with it? And most urgently, are there more? We're living through the observation window. October 29, perihelion, happens in 2 days. By the time you hear this, it may have already occurred. JWST observations begin November 4. Earth-based resumption of tracking starts around November 11. December 19, closest approach to Earth. The 16th of March, 2026, Jupiter flyby, observed by Juno. We're on the timeline. This is happening. And the honest answer is we don't know what we're going to find. The smart money says natural comet. The data supports that, but the data isn't complete. We have a gap, 8 days when the object is unobservable, and that gap coincides with the most critical phase of its passage. If you're designing a mission and you want to do something without being seen, that's when you do it. If you're a comet and you're going to break apart, that's when it happens. Either way, November tells us the answer. Here's the thing about being a scientist. You follow the evidence. You don't assume. You don't jump to conclusions. You measure. You calculate. You test hypotheses. You let the data speak. And when the data is incomplete, You acknowledge uncertainty. You say, we don't know yet. We need more observations. Let's wait and see. That's the right approach. That's how we avoid chasing phantoms. But here's the other thing about being a scientist. You stay open to possibilities. You don't dismiss the improbable just because it's uncomfortable. You don't reject a hypothesis just because it's extraordinary. You weigh it against the evidence. You ask, what would it take to confirm or refute this? You design tests. You make predictions. And you watch. Right now, we're watching. 3I Atlas is teaching us something. Whether it's teaching us about comets from other stars, or teaching us that we need to expand our search parameters for signs of technology, we'll find out soon. Are we alone? That's the question. It's the oldest question. Every generation asks it. Every culture has myths and stories about beings from the sky. For most of human history, the question was philosophical, theological, unanswerable. Now it's scientific. We have telescopes. We have spectrometers. We have spacecraft at Jupiter and Mars and orbiting the Sun. We have detection networks scanning the sky continuously. We have the tools to answer the question, or at least to start finding evidence. 3I Atlas is a data point, one object, 3.5 months of observations, perihelion in 2 days, post-perihelion monitoring starting in 2 weeks. By the end of the year, we'll have a much clearer picture. And if the picture shows a natural comet, that's fine. That's science. We learned something. If the picture shows something else, everything changes. Stay on this timeline as this unfolds. November is when the answers start coming in. Subscribe if you want to stay updated, because the observation schedule is packed and data will be released incrementally over the next few months. JWST observations in November. Hubble spectroscopy. Ground-based tracking, closest approach to Earth in December. Juno observations in March. This is a multi-month campaign, and every observation adds information. By February 2026, when JWST data downlinks, we'll know if anything separated from the nucleus at perihelion. We'll know if the trajectory changed. We'll know if the comet behaved as predicted or if something unexpected occurred. One last thought. Whether 3I Atlas is a rock from another star or something more, its existence proves that interstellar travel is possible. Material moves between stars. It happens naturally through gravitational ejection. A planet encounters a giant planet, gets flung out of its system, wanders the galaxy until it encounters another star. We've now seen 3 such objects. 1I Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas in 2025. The Vera Rubin Observatory will find more. Within a few years, we might discover a 4I, a 5I, maybe dozens. The galaxy is full of wanderers. Some are natural, some might not be. And the only way to know is to look closely, to measure carefully, to rule out the conventional before considering the extraordinary. That's what we're doing. That's what science does. We observe, even when we're uncertain. We measure, even when the data is incomplete. We question, even when the answers are uncomfortable. Because observation, measurement, questioning, these are our best instruments for finding truth. And if the truth is that 3I Atlas triggered something we don't understand yet, then understanding it becomes our next priority. The timeline is set. The observations are scheduled. Now we watch and see what November brings. What do you think? Is this a comet following the rules of physics through our solar system, or are we looking at something designed to follow those same rules but for different reasons? Comment below. Let's discuss this while the object is still in play, because 2 days from now, perihelion happens, and we won't have eyes on it. When it comes back into view, we'll know more. Until then, we're living in the uncertainty. And sometimes, that's exactly where discovery lives.